5 square root of 11 plus 7 to the square root of 4.
All right, hold on to that thought. Michael, are you back?
Yes.
Awesome. How about Mark? I see Adrian, thank you. Yemi, thank you.
I'm back.
Sumi, Elsa is, Damilola is, Ola is, Jaime is.
I'm back.
Thank you, Elsa. All righty. So 421. Let's see what we can do in this next 19 minutes. So when I say higher order radicals, we're talking about radicals beyond square roots, such as, let's say this radical is the cube root of x to the 13, and they want this simplified. Most of these radicals want you to simplify them. Okay, Olu, I have at least 2 pages from you, thanks. So simplify, it works the same way. We're gonna try to divide the index into the exponent. This happens to be a case, Jaime, where you see the index. The index is 3. So we're gonna do the same thing. Same thing, we're gonna divide the index into the exponents. So the number of times the index goes into the exponent, divides into the exponent, that's going to be what this exponent is here outside the radical, and any leftovers stay inside the radical. I want to mention this, however, if you can see this 3 is the index in your answer, the 3 must be as part of the answer in the index. So if you see it in the problem, you see the index in the problem, you must see the index in the solution. Now, the number of times the index goes into the exponent, that goes here. And that number is
4.
4, thank you. And what would be left over?
1.
1 would be left over. So we normally don't put the 1 here, of course. So you would just write the final answer as x to the 4th. And then the cube root, you got to put that 3 here. This 3 has to be here, x. That's how you would simplify a higher power index. One example. Let's call that example 1. Questions on example 1, please? If not, example 2, let's try this. The 4th root of 16x to the 12th. So here's a higher root, higher root. So the way these higher roots work is you divide the index into the exponent. But when we have an integer, I'm going to suggest this. For integers, use a factor tree. What is a factor tree? What you do is you take the integer that's in the radicand, 16, and we're going to break it down into the prime factors. So you could use 8 times 2. 8 breaks down to 4 times 2. 4 breaks down to 2 times 2. So here's the factor tree, and these prime numbers are the leaves of my tree. So all of this becomes 2 to the 4th power. So this 16, I'm going to be writing as 2 to the 4th power. So here is where we do the rewrite. For your 4th root here, change 16 to 2 to the 4th power. So we'll have 2 to the 4th times x to the 12th inside of this radical. So again, I rewrote this 16 to a prime number with exponents. X to the 12th, I kept the same. So I'm going to divide the 4 into this exponent. I'm going to divide the 4 into that exponent. So since this is 2 to the 4th, and the 4 is the index, then 2 comes out. 2 to the 1st comes out. Other thing that comes out, 4 goes into 12 3 times. X to the 3rd comes out. There is nothing left over. So that would be reducing this radical, and there won't be any radicals left over. So there would be no root indexes. So when you have numbers, integers in a higher index, I'm suggesting using the factor tree. Is there a question on example 2? Okay, I would like to do example 3. These are all higher powers, so let's go with the 4th root index again.
I'm sorry, Professor, I don't understand the one you just finished now.
Okay, we had 16x to the 12th. So I took this 16 and I broke it down to prime numbers. So this 16 is 2, and we have 4 of them. So that's 2 to the 4th that I put inside the radical. So this 4 will cancel out this 4. So the 2 will come right out of the radical. This 4 goes into 12 3 times. So x to the 3rd comes out of the radical. There's nothing left over. So that would be the final answer. And
Okay, I understand now.
is that better?
Yes, thank you.
Okay, thank you for the question. Anybody else? Okay. Let's try a larger number. Let's try 625. P to the, this is 14th. So we want to simplify this. That's a fairly large number. So we're going to use a factor tree again. So over here, a factor tree. We got to break down 625. So I need 2 numbers and multiply the 625 And we're going to keep working this out until we get prime numbers.
5,
You said 5
5.
times
It's 25.
say again.
25.
25.
I heard two numbers. I heard two different things. I thought. When? What did you all say?
5 times 125.
120. Okay, thank you. 125. Okay, that's a prime number. This is not. So let's break down this 125. 5 times
25.
25.
Yes.
Okay, that's a prime number. That's not. So that's 5 times 5. So we are down to our prime numbers. So this 625, I'm going to rewrite this as 5, 1, 2, 3, 4 to the 4th power. That's what I'm going to put here in the radical. So let's rewrite, put the root index, make that 5 to the 4th, and keep the p to the 14th power. So far, so good. So this 4 divides into this 4 evenly. So the 5 comes out of the radical. This 4 does not go into 14 evenly, but how many times does 4 go into this? That's going to be an exponent. So 4 divides into 14
3 times.
3 times. So that comes out of the radical. What's left over?
To the power of 2.
2. 2 is left over, and we keep our root index. So this 4 is the root index, because that was the root index here. So this 4 divides into 14 3 times, and the leftover, 2 left over, that goes inside the radical. So this would be our answer to that one.
Professor, I have a question.
Yes.
So why do we have to put the 4 back in this? Because we already took out the 4 from the both side, outside, and the one
Okay.
in. So why do we have to bring it back again?
Because this 4 is part of the index. So if it's
Yeah,
part of
but-
the, if it's part of the,
I'm sorry, the initial one, we didn't have to put the 4, the one we just did.
oh, here,
Mhm.
okay,
Because
that's
4 divided evenly into all parts.
yes. If the index divides evenly into those exponents, you won't have any leftovers.
It's kind of
Okay.
like a fraction if you think about it. You have to
So-
keep all parts of the fraction at the end if it doesn't divide down to its whole form. So it's kind of like a fraction because it didn't divide down to its whole form. So you're still stuck with the 4 at the beginning of the equation.
So if you have any leftovers, the leftovers stay inside the radical. And as long as you have a radical, whatever index is there has to remain there.
Okay.
In this problem, there were no leftovers. No leftovers, no radicals.
Okay.
That's fine?
Yes, it is.
Okay, good. Now, since Kathy brought it up, I was gonna do one more with these higher powers, but I'll go ahead and do one of these for Kathy.
Yes, please. Help.
This is a sneak preview for next class. The next class is going to be combining radicals. Just an introduction. We combine radicals we combine as though they were like terms. And we'll do much more with this on Friday, but she wanted to mention it now, so be it. So here's, for example, so if we have x plus x, those are like terms. So that'd be 2x. We would just add the coefficients. So this one coefficient, this one coefficient. So if we have 7 cube root of x plus 2 cube root of x. These are like radicals because they're the same radical, same radicals, same radicands, same index, same root indexes. So when you have like radicals, we will combine them by combining the coefficients. And the radical stays the same. So we just combine your coefficients. Sometimes, and this will be the last one example that we do, because you will be seeing this more so, they may say add square root of 48 plus square root of 12. None of these radicals here are the same. These are not like radicals, but if we can simplify each of these, maybe they will be the same. So this 48, I'm going to break this down to 16 times 3. The 16 is the largest perfect square here. I'm going to change this 12 to 4 times 3. 4 is the largest perfect square in 12. So the square root of 16, that's the number 4. And this square root of 3 stays in the radical, because that's not a perfect square, that stays in the radical, plus, and this one, the perfect square is 2. So 2 will come out. Square root of 4 is a 2. This 3 is not a perfect square. That stays in the radical. And now, those are like radicals. So for like radicals, we combine the coefficients, 6. And the radical stays the same. So this is an example of combining, or some may say adding and subtracting. Adding and subtracting radicals. We'll do much more with this on Friday, but I certainly want just to show you how to work some of the higher powers as well. Thank you for your time, your patience, and for sticking around and coming back. Stay safe. Take care. See you Friday, okay? Thanks, everybody.
Thank you.
Have a good day.
Have a great day.